Each of the following trig functions can be written as a ratio of other trigonometric functions. So if we start with cosecant, we know that cosecant is 1 over sine x. Therefore, sine can be written as 1 over cosecant x. Secant, 1 over cosine of x. And then cosine, secant, 1 over secant of x. Cotangent and tan have two options. Cotangent can be written as 1 over tangent of x. And then tangent can be written over 1 over cotangent of x. However, we know that tan is sine over cosine. So this also equals sine of x over cosine of x. And therefore, cotangent of x also equals cosine of x over sine x. Okay, so the Pythagorean theorem is stated as x squared plus y squared equals 1. So if we relate this to our trig functions, we can say that cosine squared of theta plus sine squared of theta also equals 1. So this is a Pythagorean identity. Then if we were to divide by cosine squared of theta, we would get the original as stated above, and when I divide by cosine squared theta, I'm going to have another identity just by rearranging. So if we look above, well, we know that cosine squared theta divided by cosine squared theta is 1. And then if we look above, we know that sine over cosine is tangent, so we can say tangent, but it's squared theta, because if sine squared divided by cosine squared, then it's going to be tangent, but it's tangent squared. And then we also know that 1 over cosine is secant, so we can say secant squared theta. So we just created another trig identity, and we can create one more. So if we were to divide by sine theta, let's see what would happen. So cosine divided by sine is cotangent. So cotangent squared theta. Sine divided by sine is plus 1. And then 1 over sine is cosecant squared theta. So from the original cosine squared plus sine squared equals 1, we can create two more Pythagorean identities. We can also make a couple more identities. So based off of the one above, if you view this in the 3 columns, then we also can say, okay, well, what does cosine squared of theta equal? And if you just subtract sine, it equals 1 minus sine squared theta. So then, if we also took the square root, we know that just cosine of theta is equal to the square root of 1 minus sine squared theta. And we can do the same thing with sine. We can say, okay, well, sine squared theta is equal to 1 minus cosine squared theta. And then again, I can take the square root of 1 minus cosine squared theta. So this actually follows the same pattern all the way through. So just from this one identity that we found above, we can now make 4. 4 more from that. And we can do the same thing with the rest. So that's what we're going to do. So here are all the other identities that we can make from the 3 that we found before. We also have even and odd identities, and these identities arise from the symmetry of the basic trig functions. So looking at the sine function first, we have symmetry about the origin, or around the origin, you could say. So what does this mean? This means that we have odd symmetry. And the notation for odd symmetry is f of negative x is equal to negative f of x. For our cosine function, we have symmetry over the y-axis. So it's reflected over the y-axis, which means we have even symmetry. And that notation was f of negative x equals f of x. And then our last one, our tangent function, is the same thing as our sine. So it has odd symmetry about the origin, f of negative x equals negative f of x. So now we're going to walk through some techniques when we verify trig identities. Now, it's important to note that we're only going to work on one side of the equation. As you can see below, it is easier to work on the more complex looking side, and you cannot move terms from side to side. And you'll see how I set it up, and if you set it up the same way, then you will stick with all of these rules and then be successful. So the first thing that we are going to talk about when verifying trig identities is that you can distribute. So I'm going to distribute the sine function. Now my left side is the more complicated looking side, so that's why I'm choosing to begin on the left side. So then when I distribute, I will have sine of theta times cosecant of theta minus sine squared theta, because we have sine times sine. And then this equals our right hand side. So the more when I write RHS, I know that I'm not going to move things to that side. It's going to stay equal to our right hand side the whole way down. Okay, so we need to first recognize that we can simplify sine times cosecant because we have a reciprocal. So we can rewrite this as sine of theta times 1 over sine of theta. And we want to do that because you notice they cancel each other out. So then we're left with 1 minus sine squared theta. Now we want it to equal cosine squared theta, so if you look at your Pythagorean identities, then 1 minus sine squared theta equals cosine squared theta. So you have to go one more step further to verify, and our right hand side is cosine squared theta, so this is where we end. So we're going to do that one more time over here for B. Again, the left-hand side looks more complicated, and we're going to distribute, and we're going to have cotangent of x times secant of x plus cotan of x times tangent of x, again equal to our right-hand side. Once again, we see a reciprocal with cotangent and tangent, and with cotangent and secant. So, with both of them, we can write cotangent as cosine x divided by sine x times 1 over cosine x plus, now I'm going to write cotangent instead of like before cosine over sine. I needed to cancel with tangent, so I'm going to write cotangent as 1 over tangent of x, and then I just have tangent of x left over. So now we can cross off some things. So we have cosine over cosine and tangent over tangent. So we are left with 1 over sine of x plus 1, which is equal to our right-hand side. So we need it to be cosecant, but we know that 1 over sine is cosecant. So we have exactly that, but we need to write it just like this one more time. So that the last thing I check at the bottom is whatever RHS stands for. So in this instance, it stands for cosecant x plus 1. I need to see that on the left. You can't stop and let me assume that I know 1 over sine is cosecant. So you have to go all the way down. Now we're going to do the opposite and we're going to factor. So if we look at number 2, this left-hand side looks the simplest. So we're going to start with that. And we're going to make sure that right-hand side turns into 1. So if I factor, the factor that both of these share is cotangent. So I can pull out a cotangent squared actually. So I have cotangent squared of x. So left over I have secant squared x. And since I took cotangent squared x out, I have a 1 left over. So looking at our Pythagorean identities, we have that the left-hand side can equal cotangent squared x, but secant squared x minus 1 equals tangent squared x. And I'm going to pick that out because cotangent and tangent are reciprocals of one another. So therefore, we can simplify. And we have our left-hand side equal to 1 over tangent squared x times tangent squared x. So those cancel out. And my final line needs to be that my left-hand side is equal to 1. For B, we can actually factor out on the numerator and on the denominator. So, again, the right-hand side looks less complicated, so that's what we're going to set it equal to. So in the numerator, I'm going to take out cosine of x, and I'm going to be left with cotangent plus 1. And I can take out cotangent on the denominator. And I'm going to be left with cotangent. Oh, nope. Be left with 1 plus cotangent of x equal to my right-hand side. So right now we can simplify because we're multiplying these, and cotangent plus 1 is the same thing as 1 plus cotangent. So this is what we're left with. And we're actually going to use the reciprocal next. So I can say that cosine or I'm going to keep cosine and say that cotangent is cosine divided by sine. And then if we write this as a multiplication problem, we're going to say cosine of x times the reciprocal of the bottom, so sine x divided by cosine x. I'm running out of room at the bottom here. So then my cosines simplify and they divide to give me 1. So I'm left with sine x, which is equal to my right-hand side, which is what I'm looking for. Okay, so now we are going to multiply. So if I have sine x minus cosine x squared, I'm going to write that twice. And what I'm actually going to set this equal to is my right-hand side. Even though you might think they both look complicated, I can work more with the left-hand side. So I can write sine x minus cosine x and just write it twice. So when I do this, now I can distribute, or I can FOIL, and I will have sine squared x minus 2 times cosine x sine x plus cosine squared x. So this is the only way that I can now, so on the right hand side you see I have sine times cosine in some fashion, and distributing like this is the only way I can get cosine and sine together like that. So that is why I chose to go with the way that I did and multiply. So I'm just going to quickly reorder these so we can have it kind of set up like our final answer. And I'm going to pull the sine squared of x plus cosine squared of x out, because I see those two as part of this function, and I know that that is a Pythagorean identity. So that's what I want. So sine squared x plus cosine squared x equals 1. So now I have 1 minus 2 times sine x times cosine x equals my right-hand side. So now while I'm looking at this, I need to make sine, everything looks good except the fact that I have sine of x instead of sine of negative x. However, knowing our odd identities, and then in our odd identities it stated that negative f of x, I'll write it down here so we can look at it. Negative f of x is equal to f of negative x. Well, I need this, and I started with this because I have this minus right there. So now I can say, okay, if I take away that negative or that minus sign and make it a plus sign, everything else stays the same, except now I can say and apply that negative to sine of the negative x. And if I do this, this is what my right-hand side equals. Okay, so for B, it is already a binomial times a binomial on top instead of me having to create one like we did for A. But what I also noticed is that I have a plus and a minus. So this is going to appear to look like the difference of two squares after we multiply. So if I multiply secant and secant, I have secant squared x, and then I have plus secant times tangent minus secant times tangent. So they add to give you 0, and I'm left with tangent times negative tangent, which is negative tangent squared of x, all over cosecant of x. And yes, our right-hand side looks much simpler. So now I'm going to use the Pythagorean identity, and I know that secant squared x minus tangent squared x is 1. over cosecant. And then I know that if I apply the reciprocal that we know so well, that 1 over cosecant is actually also equal to sine. And this is what we were looking for. Okay, so our last technique here is that we can use is making a common denominator. So if I want to look at A, I need to add those two functions together, but I can't do that because they don't have a common denominator. So my left-hand side is much simpler. So I have my left-hand side equal to sine squared of x divided by cosine of x plus, and then what I'm going to have to do is I'm going to multiply up here times cosine x on the top and the bottom so that I can create a common denominator. So then my new numerator on this right term becomes cosine squared x, and then over the denominator just cosine of x. So now I can add them together, which I will. And if you notice, now we have sine squared x times cosine squared x, and that is a Pythagorean identity. So that equals 1. So I have my left-hand side equals to 1 over cosine of x. I'm looking for it to all be set equal to secant, and we know that secant is the reciprocal of 1 over cosine. So my final answer, or my last line, is the left-hand side is equal to secant of x, which is what we wanted. Okay, so for B, it's a little bit more complicated, or it's more complicated because we have both of these terms, the first and the second, both need something to have a common denominator. So the left side is actually the more complicated side. So what we're going to end up doing is we are going to end up multiplying this left term times sine x over sine x, and then the right one times secant x times secant x. So if we write that all together, we will have sine x times cotangent of x minus cosine x times secant of x all over sine of x times secant of x. So now, if we use our reciprocal, if we use the reciprocals, we can adjust our cotangent and our secant in the numerator. So I'm going to have sine of x times cosine of x over sine x minus cosine, that doesn't change, and then times 1 over cosine. So that's just the numerator, so this whole thing is now going to be over sine of x times secant of x. And then we can simplify now, because we have sine divided by sine and cosine divided by cosine. So after we simplify, we have cosine of x minus 1 all over. Okay, so right now what I'm also going to do is another reciprocal. Now in my denominator. So now I'm going to have sine x times 1 over cosine x. Well, it doesn't help me cancel anything out, but if you look at the right-hand side, which I have lacked to write equal to, if you look at the right-hand side, we need tangent on the denominator. So again, sine over cosine is tangent. So we have cosine x minus 1, which is our numerator, so we're good. And then we have sine over cosine x, so now I have tangent of x. And that is equal to our right-hand side. So going through all these techniques, the first one we did was you can distribute with trig functions. You can factor them. You can multiply or expanding, which was a little different than our distributing, which is just with one term. And then you can also make common denominators. All remembering all the identities we created at the beginning and our reciprocals. So we have reciprocal identities, Pythagorean identities, and then even and odd identities. So with all these tools, we're going to be able to verify trig functions.